Hello, we're going to demonstrate finite state machines, in particular logic label finite state machines. And in this video, we're going to make a very small case study so that when we run this machine, you see a behavior that is similar to this. In one state, the machine is in the state initial, and in the other state is in the state pong. And while in initial, it moves a little marker right, and when it's spun, it moves the marker to the other side. So that's what we like to demonstrate how we build this. State machines are ubiquitous in computing, so I'm going to spend some time in this picture because state machines are usually also presented as drawings, but they are also encoded in many ways in many programming languages and in many modeling behavior of computer systems. State machines, as the name indicates, are made of states. States last in time and in the drawing are represented as big squares boxes. So machines are in a state, but they move to another state by transitions. Transitions are indicated by arrows. In logic label finite state machines, the only thing that can go labeling a transition is something that evaluates to true or false. We call that a predicate or a Boolean expression. Finite state machines start from the state that has an arrow from outside, usually from a bullseye. In this case, the initial state is the state ping, which we see here the label for the state. In this case, this machine is going to start in the state ping and run the code there, and then when the transition out evaluates to true, it will go to the state pong. When you arrive to a state, what you always do is the code in the onEntry section. Then you evaluate the transitions that depart the state. If none of them evaluates to true, then the code in the internal section is evaluated. Only when a transition evaluates to true, the code in the onExit section is evaluated. And then, as we arrive from another state into a new state, then the onEntry of this state is evaluated. It's important to remember that more than one transition can be out of a state, and in that case they are in sequence, so they are in order. And also, more than one machine could be executing concurrently. They exchange turns after finishing a section in a ringlet. Because logic label finite state machines in C++ can be compiled, and usually they can be compiled with bmake or make, but in this case we're going to do it with ROS. The first thing we're going to do, I'm going to create a workspace. A workspace is just an area where you're going to build projects. It's similar to a project space or a workspace in Eclipse or in NetBeans, for example. And I'm going to go into it, and a workspace doesn't make any sense if it doesn't have a structure, and typically the source files that are going to be compiled or so on go in a subdirectory source. So I'm going to make that one as well, and we have it here. And in source, I'm going to create my machine. Now machines in C++ get scheduled by a scheduler called LLFSM that is downloadable from the MyPal downloads website, and it's here, and we're going to need it in a moment, but for the time being I'm just focusing at the moment on the structure of a catkin workspace. So remember, a catkin workspace has some name. It's actually whatever you want to call it, but it does have to have a directory source where you put your packages. And packages, you can think of as a series of programs with one purpose. In this case, it's just going to be just our machine. Now, in the how-to documents for using machines, we do have the instructions catkin create package. This is the line of code that we're interested in here. You see the command catkin create package. Let's copy that. Inside the source of catkin workspace is that we create a package. I'm going to call it ping pong. And if you look at it now, there is a folder called ping pong. And if you look into it, there is already CMake list file there, plus a package XML, plus a source, plus an include. The beginner's tutorial tells you a little bit about what does package XML do. Basically has to define who the owner, maintainer, and so on and some dependencies among packages. And these files here, usually you edit in the beginner's tutorial because this is actually the driver file for Catkin. Catkin is kind of a preamble for software manager called CMake. Typically in C++, in the source files are put in the source directory and the include files are put in the include directory. We'll have an opportunity to see a bit about that when we compile our machine. So now here you can see that we are in our workspace. In the source part of the workspace, we have a package called ping pong. If we look at the package itself, we have the structure of a package with the package XML, and that leads an include and a source. So we're going to go into it and make a directory called machine, just because it's convenient to put the whole entire logic label finite state machines in this subdirectory. In your beginner's tutorial for ROS, you get to see other folders, for example, for services or message folders for topics. We're going to go here into machine, and this is where we're going to build our machine. We're going to build our machine with a very simple Java application called myEdit. You can also download that one from here, so you can use it here and it runs. So in a sense here we're teaching you also a little bit how to construct machines with this simple editor. So here is the editor, new, and double click, so it takes me into the source, into package, into the machine I just really created. I say OK, and as I said, I'm going to call it ping pong. If I say file save and I go back to our structure that we have here, you're going to see that it creates a directory called ping pong machine. If I look at that directory, there's already a bunch of files. So you have to understand that a finite state machine is an encoding of a behavior made of many files, several files for each state. So let's put some code in the first state. So in the state, and this is how we just paste this code here, and I'm going to save that state, and I'm going to say I need a new state, and that one we're going to call it pong. And in pong at the moment, I'm going to put the same statement, but I'm going to make 0. Save the state, and I'm going to go to a transition. I'm going to add it. I'm already in pong, so I'm going to go to initial. And the predicate I want to put is, it's a predicate that LLFSM supports. It comes from augmented time finite state machines, even from the subsumption architecture of Brooks, called after, and this becomes true after 1 second. I'm going to save the state. I'm going to go back to the state initial, and in initial I'm also going to add a transition, but now back to pong, and the transition I'm going to add is the same. Now, because we're using the variable I need to declare that, so I'm going to put it here as an integer. And I have a little reminder here about what to do in the includes. Maybe I don't include anything and see what happens. I want to show you how to fix errors. Save the machine. You can do the same trick I just did a moment ago. And now you see that there is other things for the new state that I created called pong. And actually you can see the transitions as well. For example, I can see this transition. So now I'm going to compile this machine and run it. And be patient with me because I'm going to commit a series of mistakes so that you see what type of errors do we get. We need to download a script. I'm just going to download it now, save it, and then move it here. This precisely is what it's going to do, is split all these files we have seen and put them in the right place for the source, for the include, and also generate a suggested file for all the compilation instructions that should be here in the driver of catkin to create the CMake files and so on. Extract because it comes compressed, and I'm making it executable. And if I do a machine and then parameter the machine, several things happen. First of all, you're gonna see that if I look up, all right, we have the include and the source. The include now has the include files of the machine ready there. And if I look at the source, you also have some source files for the machine already there. However, consider the place where we work for the machine, the actual machine here. We still have it actually open over here. We have the suggested file, and the suggested file is the proper CMake list, but not with the dependencies. So because of that, we open it, we copy the dependencies, we actually use the proper one, but we override the dependencies. And once we do that, we have to copy this one, copy the suggested one, and override the default one. And now we are ready, in a sense, to compile. So in order to compile in Catkin, I'm going to open a new tab. I'm going to use this for compilation. Let's go to the root of my workspace, and I'm going to do catkin make. And the first thing you're going to observe is that it tries to compile ping pong, and it's going to complain that it does not find a package in depends on LLFSM. So that's here when we do really need the libraries of this guy. I'm going to bring it down, save it. It's going to land in my downloads, another tab, go to my downloads and extract the catkin workspace that you see there. Okay, that's been extracted. Now we have to bring them here, those packages. We only have this package, so I'm gonna move them here. So I'm gonna move from downloads, catkin workspace, source, LLFSM to here. Another one that we need is called LLFSM, and we also need simple whiteboard. Don't be alarmed, this is just infrastructure for executing the C++ machines as compiled machines. So now we can compile again, and because of catkin trying to parallelize, you may have things like things do not succeed for a moment. You see it tries to parallelize, so try a couple of times until you get a genuine error. This is just about here we have our first error, or actually first two errors. So when your package has a C++ error, you get something like this. The error that we get is a missing declaration and a missing of the after. These are errors that derive because I didn't put the corresponding includes I should have. We need this so we can use the macro after to label a transition, and we need this to use the standard output files and so on. So we save this. Now when you modify a machine, not structurally, we didn't add any states. The only thing you need to do is go by here. Remember where we need to be? We need to be in our package ping pong machine. We don't need to replace or update this file. Do not update it unless you change the number of states or where does a transition go. But if we only change the contents of the C++, the only thing I need to do is the split of the files. And so once we do that, we can try to compile again. And this time the machine has compiled and it's an executable. So I'm going to leave the screen for compiling. I'm going to open another tab, And when things compile on catkin, first of all, the build is where it puts all the CMake scripts to actually build the thing, and that's why it tries to do things in parallel afterwards. The build is when the actual products are finished. So we're gonna go into the build, and in lib is usually where it places executables or either as library or independent programs. So we're gonna go there. We have CLFSM plus the libraries of CLFSM and the usimple whiteboard. So this is what actually was produced by the download of CFLM, but our machine is this one already compiled. This is a directory just created for CLFSM to handle when we have more than one executable machine. So what we do is copy this library who has been compiled for our machine, and we're going to put it in a subdirectory Linux. Sometimes we compile for a robot or a different type of operating system. Because we compile for Linux, we remove the lib. Once we have that, the scheduler CLFSM has been compiled is inside this directory, and at the moment I'm just going to put the name of the machine and run it. And you see it switches between the states more or less after a second. Let me just point out that there is an option for CLFSM called -b, which allows you to verbose see how it's changing from one state to the next. We're in a position to do more sophisticated code for our states. I'm going to take out the fact that we print to the standard output, scroll down a bit and do something in the internal section of my state Pong actually. To choose a state, I go to states, Pong, and I want to go up a bit, eliminate this line. In the internal, again, don't worry too much. The purpose of this video is not to teach C++. I have already prepared for the particular output we're going to generate. Save the state. We go back to initial, and we put it in the internal section here. State save, and again we go to the tab where because we changed the C++ code, what do? We have to repartition. Now have to recompile. So here we go and compile, and we had an error. And again, we have a little variable here that has not been declared. So actually, it's an error again I put in purpose, already prepared for that. And actually, we're going to need also change because now we're using files. So we're going to need to do this as well. So probably there's more errors, but we're going to fix all the errors in one go. So we're going to do that by updating the includes, save the includes file, just to be sure save the machine. Again, because we modified the C++, we have to do the split, then we compile. It has compiled, so in a sense, if we go here, all right, don't do immediately this because we haven't copied our library. So you have to go back to this command, remember that copies the library into the corresponding place. And then once you have that, I'm gonna actually run it, not verbose, so we get the effect that I promised you at the beginning of this video. I hope you enjoyed this. Thanks.